Well, this is a really crummy way to measure the curvature of the universe. Why don't we measure it using geometry directly? So we can measure the curvature of the universe. And to do that, I want to ask you, how would you measure the curvature of the Earth if you couldn't go outside the Earth and see it from a satellite, or you couldn't go around it? Very simple. You draw a triangle, and you ask a European high school student, what's the sum of the angles in a triangle? They'll tell you 180 degrees, but you say, that's fine, you learned your geometry from Euclid. But on a curved surface, it's very different. On the surface of the Earth, I can draw a triangle that's very different. I can go along the equator, I can make a right angle, go up to the North Pole, make another right angle, and come back to the equator, and I have a triangle with 3 right angles. 3 times 90 is 270. So if I made a big enough triangle on the surface of the Earth, I could measure the curvature of the Earth. I wouldn't have to go around it. Now it turns out, even though this is a 2-dimensional picture, the same is true for a 3-dimensional curved universe. If I had a big enough triangle and I measured the angles in a triangle, I could measure the curvature of space. And we've been able in the last decade to find a big enough triangle. And I want to spend 5 minutes telling you about that, because it's the most important, probably, observation in all of cosmology. The observation of the cosmic microwave background radiation, the afterglow of the Big Bang. One of the many reasons we know the Big Bang actually happened. What do? When we look out at space, we look at galaxies that were, say, 1 billion light years away and they're 1 billion years ago. But if we know that the universe is 14 or 13.72 billion years old, if we look far enough, we should see the Big Bang, right? Well, we can't see all the way to the Big Bang, because between us and the Big Bang, there's a wall. So like this wall here. Not really hard like that, but the fact the wall is opaque means I can't see past it. If I go looking back in the universe, it was getting hotter and hotter and hotter, and at a time when it was 100,000 years old, the temperature of the universe was 3,000 degrees. Slightly warmer than Phoenix this week. And at that temperature, the radiation is hot enough to break apart atoms, hydrogen in particular, and break it apart so the protons and electrons are separated. You have a charged plasma, and a plasma is opaque to radiation. So we can't see back past this time, simply because the universe is opaque. But that's okay. The reason I can see that wall is that light bounces from those lights there off the atoms on the surface of that wall, is re-radiated, but the air is transparent, so I can see all the way to the wall. If we run this film forward, as the universe is opaque, 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 and then it becomes neutral, the atoms, protons capture electrons, neutral matter is transparent to radiation like this, and that means I can see all the way back to that radiation coming at that surface. A prediction of the Big Bang is there should be radiation coming at me from all directions, coming from that surface called the last scattering surface. It was 3,000 degrees then, it's 3 degrees now, and it was the radiation that was discovered by accident in New Jersey, of all places, by 2 people who didn't know what the hell they were doing. And they won the Nobel Prize anyway, because they discovered the afterglow of the Big Bang. Actually, another aside, I can't help this because this is amazing, and if you ever want to convince skeptics, you won't ever convince people of this who don't believe it anyway, but you've all seen this radiation. Or at least those of you who are old enough to be as old as me, before cable TV. Remember when the TV stations used to end? And then to be static? 1% of the static on your TV screen is radiation from the cosmic microwave background. So you've all seen it. Okay? But it's amazing, we didn't even know about it until 1965. Okay? In fact, it had been predicted by people like George Gamow, but people had forgotten that. In any case, as interesting as that history is, on this surface is a very important scale, 1 degree. Why 1 degree? Because that represents a distance of 100,000 light years. Now, the surface existed when the universe was 100,000 years old, and Einstein tells us no information can propagate faster than light. So that means nothing that happened over here at that time could ever affect anything that happens over here. But more importantly, if I have a lump of matter that's this big, it knows it's a lump of matter, so it starts to collapse. But if I have a lump of matter that's this big across at that time, it doesn't even know it's a lump, because gravity can't have traveled across it. So it's like Wile E. Coyote in those cartoons when he goes off the cliff. He waits a while before he collapses, okay? And such large lumps won't collapse. So the biggest lumps that can have collapsed at that time will be 1 degree across, and that gives us a cosmic triangle. Because we have a ruler that's 100,000 light years across, the size of the largest lumps, a known distance away from us, and in a flat universe, light rays travel in straight lines, and we can calculate the angle on our eye subtended by a 100,000 light year across ruler at that distance. It's 1 degree. In an open universe, light rays diverge as you go back in time, and the whole thing might be ½ a degree. The ruler will look smaller. In a closed universe, light rays converge as you go back in time. The ruler will look bigger. So we just have to look at that microwave surface, try and measure the lumps, and see are they 1 degree, ½ a degree, or 2 degrees. We've been able to do that in the last decade. This was the first experiment that did it. It was called the boomerang experiment in Antarctica. It was a balloon, took this microwave radiometer above the Earth's surface to look at this radiation, take a picture of it, and this balloon went around the world, which is easy to do in Antarctica, okay? And it took a picture. It's really easy in the South Pole. You just do this. But anyway, and this is the image. Well, this is a false color image of that. I put it, superimposed it on the original image. This is the image of the microwave background, the hot spots and cold spots in the microwave background. And these are the lumps in the early universe. And the question is, how big are they? And here's a different false color image of the same region. And we can compare this with universes we create on computers. Here's a closed universe where the lumps are bigger. They should be this big across. If they're 100,000 light years across, they should look that big. Well, that's bigger than these lumps. Here's an open universe, and you can't see the resolution of the screen isn't that good, but the average size lump is about that big. Smaller than these lumps. But just like Goldilocks, in a flat universe, it's just right. In fact, it's right now, we know, to an accuracy of better than 1%. The universe is flat. It has 0 total energy, and it could have begun from nothing. And I've written a piece, although of course I got a lot of hate mail, saying that in my mind this answers this crazy question that religious people always keep throwing out, which is, why is there something rather than nothing? The answer is there had to be. If you have nothing in quantum mechanics, you'll always get something. It's that simple. It doesn't convince any of those people, but it's true. Now, great, we know the universe is flat. But if you've been awake, you realize, 10 minutes ago I proved the universe was open. There's only 30% of the stuff in the universe needed to make it flat. Where's that other 70%? Well, if you put energy in empty space, so empty space weighed something, you wouldn't see it. It's the empty space between the galaxies. You're far away from the galaxies, you wouldn't see it. But what would that empty space do if you put energy in it? Well, it produces a cosmological constant. That would cause the expansion of the universe not to slow down over time, as any sensible universe should do, but to speed up over time. In 1998, people measuring these supernovae at large distances to measure the Hubble diagram tried to see what was happening at large distances to see if the universe was slowing. Well, they all knew the universe was slowing down. They wanted to measure how much. This doesn't look like much, but it was a revolution in cosmology. I can draw a straight line through that data set there and bring the whole thing down and make it horizontal. And if the universe was slowing down, these distant supernovae should have followed this curve. Much to the surprise of the observers, the supernovae lay above the straight line. And the only way to explain this, well, there's two ways. Either the data is wrong, which it usually is, or the universe is accelerating, speeding up. And if just for fun one believed it was speeding up and asked how much energy would you have to put in empty space to make it speed up by the amount we measure it, it's exactly the amount we are missing. Everything holds together. Our new picture of cosmology is that we live in a universe dominated by nothing. The largest energy in the universe, 70% of the energy in the universe, resides in empty space. And we don't have the slightest idea why it's there. Now, that's what I just said.